Thank you for introduction and troubleshooting. My name is Konstantin Sirenko. I represent the Institute for Radiophysics and Electronics from Kharkiv, Ukraine. And my today's talk is devoted to layered structures consisting of conventional dielectrics and smart materials, namely graphene. Why graphene? Because it possesses so many intriguing properties, and for decades, from its theoretical and prediction and later practical production, it remains in a focus of ongoing research efforts by many groups, and and new applications and interesting combinations keep on appear and appear. So today talk is so in this presentation I will discuss what we have done for theoretical studies of combination of graphene with metal and dielectrics. So the outline of my talk is on the screen. I will start with formulation of mathematical problem and briefly tell the approach we use to solve it numerically. And then we'll follow the main part where I will present an interesting result we obtained for graphene dielectric sandwiches. And in the end, briefly discuss the possible applications of the obtained result. So we consider, I hope you see my mouse cursor on the screen. So in a top right corner is a schematical depiction of structures we consider. It is periodic in Z direction, layered structures consisting of dielectric and dielectrics or metamaterial or graphene today. It is enlightened by homogeneous or inhomogeneous H-polarized electromagnetic wave, which gives rise to a scattered field, which could be written in terms of space harmonics of periodic structure, above the structure and below the structure. R and T here are complex reflection and transmission amplitudes, and the scattered field is expanded in terms of space harmonic of the structure, where gamma and phi are horizontal and vertical propagation number. So to solve for the to obtain the total field, we solve the wave equation with regard to the Hx component of the field, which has periodicity conditions, because it's periodic in that direction. And we, as we write the field in terms expanded as special harmonics, we solve for R, these complex amplitudes R and T. And to do so, we employ the semi-analytical approach called method of analytical regularization. So having these complex amplitudes in hand, we mainly concentrate on on transmission and reflection coefficients, which are energy distribution between reflected and transmitted spatial harmonics. As the method is semi-analytical, it provides highly accurate and in the same time predictable solutions. Predictable, I mean, with predictable accuracy. And this is of crucial importance for the problems we face in, because the structures we study are resonant in nature, and the resonance we face there are very high quality with very high Q factors, and they manifest themselves in very narrow frequency bands. So being able to get a solution with high accuracy and high resolution is really important. In our model, we use the graphene model presented in the screen. The electromagnetic response of graphene is determined by its surface conductivity, which is in turn depends on its chemical potential. It was derived by using Kubo formalism, and constitutive parameters of graphene in the end have this form, yes, especially epsilon is the most intriguing one. It depends on frequency and also on omega p, which is like plasma frequency, which has this form. It depends on a number of physical constants, also geometrical parameters, temperature, and here is the chemical potential, which could be varied, and in varying chemical potential, the chemical potential could be changed applying static electric field, and changing chemical potential, one may control epsilon of graphene layer. So, and in today's talk, and the geometries we're considering, mostly we concentrate on graphene under dielectric slab with periodic interface, or graphene on a metal plate. Also, as secondary geometries, we consider it just a layer of graphene and the dielectric slab with periodic interface to see the influence of most these simple structures on them. So we start with just a flat layer of graphene and look at the transmission and reflection coefficients with normal incidence. For normal transmission for normal incidence is always complete, so virtually nothing interesting happens. But when the incidence angle grows to 15 degrees, we observe a very pronounced resonance at plasma frequency 0.3. And if the layer of graphene is not flat but has an uneven structure, the resonance picture becomes much more diverse. For oblique incidence, for normal incidence, there is just one resonance very close to zero frequency. In the left, we see transmission coefficient in the right and the reflection coefficient in gray color, and field distribution, field pattern for this case. And when the incidence is oblique, there are a number of very high Q resonances. You can see them in transmission or reflection coefficients. They are reciprocal, and the field distribution for some of them. Having this pronounced picture of resonances for uneven surface suggests an application. So it could be used for detection of defects in production, when instead of a flat structure we get something with uneven surface, and we could immediately tell that there are these defects having much more resonances than for a flat structure. And the same could be seen when the structure is excited with an inhomogeneous electromagnetic wave. It is like something of an electron beam flying above the structure. So there is for uneven graphene layers, resonances in reflection coefficients could be seen close to, on a frequencies close to plasma frequency, and here is its field distribution for it. Then we move to another geometry, another structure. It is graphene on a metal and thin metal plate under inhomogeneous excitation, namely the electron beam flying over this structure. And we have observed that changing plasma frequency and thus changing epsilon of permittivity of graphene, we have dramatic changes in resonance picture. So, for example, for Kp 0.3, we have very high Q resonance on a frequency close to it. It is reflection coefficient. And this chart in the right shows the direction of radiation for this resonance reflection. And when the Kp changed to 0.45, we have now 3 resonances with much less Q factor. This is the direction of radiation, and this tendency remains for a change in Kp. And next we move to our main structure of interest, which is graphene layer under the electric with periodic corrugation. We study behavior of these resonances in reflection and transmissions through this structure when we change different parameters of the structure, like thickness of graphene or the electric layers, depths of grooves in periodic corrugation of the electric, and so on. First, we start with changing the electric thickness. Those charts present reflection coefficient dependence on frequency, the lower bar, and thickness of the electric, the left scale. So we see that with growing thickness of the electric, resonances move to the lower frequencies. And varying chemical potential of graphene layer, we can place a resonance which was shown earlier close to the place where the electric resonances are concentrated, and we see the situation like shown in this inset. in the same time, changing dielectric groove depths has little effect on the resonance's behavior. So here is the transmission coefficient as a function of frequency, the lower bar, and groove depths, and not much changes with growing depths. Here we present the reflection coefficient with as a function of frequency and incidence angle. So for lower frequencies, the growing angle of incidence pushes resonance towards lower frequency, and after approximately 0.85, growing incidence angle now will push resonances towards higher frequencies. And the inset show a picture where graphene resonance meets the dielectric resonances. Also, what we can do is change epsilon of dielectric, like change the dielectric layer on top of graphene. The tendency here is that with a higher epsilon, the resonant frequency shifts toward lower frequencies, which could be seen in more general when we plot reflection coefficient as a function of both frequency and epsilon. So this movement is towards left is clearly seen for all sets of the electric resonances. It's also worth to point that losses in graphene are also crucial, and the higher this loss, the lower Q factor of the graphene-induced resonances. And after certain points, certain value of the loss gamma, the graphene resonance is completely vanishes. So it's important to keep in mind this for model reliability. The same situation in a different form for zero loss, the transmission coefficient was virtually zero, so the structure was blinded, and for loss of 0.01, it is completely transparent. In the same time, the dielectric resonances stay in place, so it could also be somehow useful for from engineering point of view. So when one have a full picture of the properties of the structure and how these properties depend on how these properties behave with changing parameters, one can predict, one not only describe this the properties, but it's possible to make guesses what gonna happen for this or that set of parameters. So one can control the behavior of the structure, and this may lead to interesting applications. So vary in chemical potential via static electric field. It's possible to change graphene's epsilon, which gonna shift graphene resonances, and they could be moved close to the electric resonances for extremely high Q transmission or reflections. Uh, the other geometrical properties that could be influenced under control are the electric substrate thickness or groove depth, and the electric permittivity. So also was demonstrated dependence on the incidence angle, which I do not have here. And with this in hand, one possible application of such structures is to use these graphene dielectric sandwiches as mirrors for open resonators. They are transparent for all the frequency range except the vicinity of Kp, and thus it's possible to design a single mode quasi-optical resonator, and its resonance frequency will be controlled via static electric field, which affects chemical potential of graphene, and thus its Kp. It could find its use in terahertz spectroscopy, plasma detectors, and so on. And another application, as I have mentioned, is defect monitoring in production of such layered structures when uneven surfaces has much more distinct and pronounced resonance picture. So I'm approaching a conclusion, end of my talk. We have successfully applied spectral methods, namely the method of analytical regularization to study new materials like graphene and in metamaterials in other studies. As it exhibits, its high accuracy is very well suits high Q and narrow band resonances common for such structures. And this allows prediction of interesting and useful properties of of devices, and the ability to control these properties leads to potential applications. So that's it. Thank you very much for your attention.